Flack math! Give me some math and I'll give you some flack. Flack math!
So today we're going to talk about vectors. And those of you who are in geometry, you guys already have a good understanding of this. And I think we've briefly talked about vectors in this class. But vectors, if you've seen Despicable Me, you know that vectors have direction and magnitude. So unlike just a typical ray, it has a direction, so what direction it's going, either measured in slope or reference angle, and it has magnitude, so how long it is. So there's a terminal point here, okay? All right, so real quick, a vector is a quantity that has magnitude, orientation, and direction. So orientation is whether it's going forward or backwards. There are several ways of expressing vector quantities, including complex numbers and matrices. Okay, so let me just start with an example here. Here's example 1. It says graph vector z whose endpoints, so I'm going to say vector z, and this is how you label a vector. So it looks like a ray, but there's only half of the arrow there. Z whose endpoints are 5 and 7, okay? So if I were to put a little graph here, oh, that's terrible, but oh well. So 5, 7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So here's what that vector looks like, okay? So this is, the directions say to graph it on the Cartesian and complex planes. So this is the Cartesian plane. So you can label this, you know, normally. But if we were graphing on the complex plane, and some of you know this, these are the real numbers. So this is the real number axis, and this is the imaginary number axis. So for example, this could be basically 5 plus 7i, okay? So this is 7i, and then this is 5 here. So the way you would graph a complex number is like a vector, okay? So you go left to right this much. So this is your real number value. And this is your imaginary number value. So this is where you go up or down. So if this is negative 7i, it would be just go down the y-axis. Okay, so it's not an x and y axis. It's a real number and imaginary number axis there. Okay, so that's graphing a vector. You can also add vectors. And adding vectors is real easy. You just add the x's and add the y's. Okay. So here's example 2. We're going to add A plus B. Okay, and it gives us A. A is, and we can give it in complex form. We're going to say 1 plus 3i, and B is 3 plus 4i. So if I were to graph it, 1 plus 3i looks like it's right there. Then 3 plus 4i looks like it's right there. So here's A, and here's B. So I can add these. And adding is, if you take this guy and you just put it where A ended and just draw like a little parallel line there, then that should give you what happens when you add them. So you go this far and then you go this far, okay? But adding is real easy. You just add the real number components and the imaginary number components, or the x and y components. Okay, so when you do that, look what happens. It looks like it ends up at 4, and then 4 plus 7i. Okay. All right, so if you can add vectors, you can subtract them, same way. And then you can multiply. So multiplying vectors is basically the dot product. And so you can use matrices to add vectors, and you can use matrices to multiply vectors. So to multiply it, for example, if here's our first vector times, and then we know how to do matrix multiplication, right? So you just multiply this by that, add them together. So your final answer is x1, x2 plus y1, y2. Okay, so if I wanted to find the dot product of A and B, so A is 3, 7, B is 5, 3. If I wanted to find the dot product, then that would be 3, 7 multiplied by 5, 3. So that would be 15 plus 21, right? Because 3 times 5 is 15, 7 times 3 is 21. So that's 36. So the dot product of those two vectors is 36. Okay. And the magnitude. So the magnitude is basically just the distance formula. So you can find the magnitude of these vectors by just applying the distance formula, because look at this. If I were to graph this, 3, 7, it would look like this. That means it goes over 3 and up 7. So the magnitude of A, and it's denoted by absolute value symbols, is just the distance formula. 3 squared plus 7, square root of 3 squared plus 7 squared. That's it. Okay. So the magnitude of A is the square root of 58. Okay. No problem. You guys have questions on vector addition, multiplication, subtraction? You guys good?
Good.
Yeah.
All right, let's move on to lesson 100. My goodness. All right, lesson 100 is about graphing rational functions. Okay, so a rational function is basically like this. F of x, it has basically, you've got a function over a function. So rational basically means, you know, it's the algebraic fancy word for fraction. So there's a fraction, but there's a function in itself on top and a function in itself on the bottom. All right. So the domain is all real numbers except for those which h of x equals 0, right? So the domain is everything except what makes the denominator 0. So whenever you have a fraction, you always have to look out for that, except for h of x equals 0. Okay, so if you had something like this, the domain is everything except the number 3, right? Because you can't have 0 in the denominator. All right, so a real number that makes a denominator, basically what that happens, when that happens, that creates an asymptote, okay? And we did talk about this briefly, but this guy, so the vertical asymptote, so this is called the vertical asymptote, is when h of x equals 0, okay? All right, so let's just try an example here. We're going to find any points of discontinuity. So basically, discontinuity is where it approaches that asymptote but never crosses over, okay? Here's example 1a. Y equals x plus 1 over x squared plus 5x plus 6. Okay, so when in doubt, factor it out. So this is how you factor this: x plus 2, x plus 3. Okay, so the points of discontinuity are where points of discontinuity where the denominator equals 0. So x equals -2 and -3. Okay? All right, well, what about this? Let's try one more. Let's find the points of discontinuity in this guy. Well, x plus 5 over x squared plus 6. Well, the points of discontinuity is just where this equals 0, so let's set it equal to 0. X squared plus 6 equals 0. Okay? So let's solve for x. X squared equals -6. X equals the square root of -6. All right, so that's x equals, and don't forget positive or negative square root of 6i. Remember, you have to take that I out of there. So these are your points of discontinuity. Okay? Now, since it's not a real number, there is no point of discontinuity. So you can, the answer to that is none. All right. So you're trying to find, moving on right to example 2, we're going to find vertical asymptotes in holes is what it says. So let's try this. Here's example 2a. This is what the function looks like: x plus 1 over x plus 4. It's already factored out for you. X minus 2. Okay, so the points of discontinuity, we already know that. The discontinuity are x equals -4 and x equals 2, right? And since there are no common factors of the numerator and denominator, you can't cancel the x plus 1 with anything, then these are the vertical asymptotes, okay? So these are the vertical asymptotes. So they're also the vertical asymptotes. Now, the reason why it had to say you can't cancel, because if you were to cancel, if this was an x plus 1 and this was an x plus 1, you could cancel those. So there would only be one vertical asymptote. Okay? All right. So let's look at B. So I want to find the points of discontinuity and the vertical asymptotes. So here's another equation: x plus 5, x plus 6, all over x plus 6, x plus 5, x plus 6. All right. All right, since there are common factors, then you basically just end up with boom, 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 1 over x plus 6, right? After you cancel those. So this is the only vertical asymptote. Because everything else canceled. But you still have these holes. You still have holes of discontinuity still at x equals -6 and x equals -5, okay? But this x equals -6 is where that is a vertical asymptote, because that's the only one that didn't cancel. Okay. All right, now this is where we get to the gist of this lesson. So the graph of a rational function has at most one horizontal asymptote. So horizontal asymptote is this. Vertical asymptote is this, okay, where a graph would approach, never quite get to, okay, and you can have that horizontally as well. So it could have this guy, okay. All right, it has at most one horizontal asymptote. If the degree of the denominator is greater than the degree of the numerator, the graph has a horizontal asymptote at y equals 0. Okay, so this happens at y equals 0. So if degree of the numerator, the top, is greater than the degree of denominator, then the horizontal asymptote is y equals 0. Okay, right here. If this was the case, then the degree of the top is greater than the degree of the bottom. If I were to multiply all this out up here, I'd get x squared something. If I were to multiply all this out down here, I'd get x cubed something. So this would not fall into this category. Remember, the degree is the highest exponent, or basically how many the degree of the highest degree term. Okay, so if that's the case, if the degree of the numerator is bigger than the degree of the denominator, then the horizontal asymptote is 0. All right, so this is still less. This is a degree of 1 up here, and this is a degree of 2 down there. Okay, still less here, degree of 1, degree of 2, degree of 1, degree of 2. So we haven't run into anything with that scenario yet. All right. So now, if the degrees of the numerator and denominator are equal, then the graph has a horizontal asymptote of y equals a over b. Now let me tell you where a and b come from. So if degrees are equal, then the horizontal asymptote equals leading coefficient divided by the leading coefficient of the denominator. Okay, so that's kind of a weird one. They call it a over b, where a is the coefficient of the term with the highest degree, the leading coefficient in the numerator, and b is the coefficient of the term in the highest degree in the denominator. Okay, so in this case, the leading coefficients would just be 1 and 1. All right, but that's if the degrees are equal. All right, so obviously there's a third example here. I can turn the page. Okay, so the third example is if the degree of denominator is greater than the degree of numerator, then this, then their, sorry, the degree of the denominator is greater than the degree of the numerator, then the graph. Okay, I think I messed that up. I reversed this. I'm sorry. If the degree of the numerator is greater than the degree of the denominator, then the graph has no horizontal asymptote. Okay. If the degree of the denominator is greater, then yes, then horizontal asymptote is y equals 0. Sorry, this is, there's no horizontal asymptote. Okay, so if the degree of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote. If they're the same, then it's basically the ratio of the leading coefficient on top over the leading coefficient on the bottom. And if the denominator is bigger, like what it was in all these, then y equals 0. So this is the case where the denominator degree is bigger than the numerator degree, so the horizontal asymptote is y equals 0. Okay? All right, turn the page. All right, so let's find the horizontal asymptotes in these examples. And I'm going to try to leave my messy notes right there. Here's example 3. Find the horizontal asymptotes. Okay, here's a 3x squared plus 2 over x squared minus 5. Okay, anyone know? Sorry that I confused you. So if you don't know, it's understandable.
Anyone?
All right, so there's 3 different scenarios where the degrees are equal, where the numerator degree is bigger than the denominator degree, and where the numerator degree is less than the denominator degree. Which scenario is this? Well, they both have a degree of 2. So remember, you're just looking at the biggest exponent on top and the biggest exponent on the bottom. That's the simplest way to put it, but if you have more than one variable, then you can't do that. But this has a degree of 2, this has a degree of 2, so let's go up here to our messy notes. If degrees are equal, then the horizontal asymptote is the leading coefficient divided by the leading coefficient. So the horizontal asymptote, the HA, is y equals 3 over 1, which is 3. Okay, so if I were to graph this, 1, 2, 3, this is where that asymptote would be. Okay, at y equals 3. All right, let's try another one. Where is the horizontal asymptote of this guy? 2x squared plus 3x plus 7 all over x minus 5. Anyone know where that is? If you can read the messy notes. Anyone know?
Doesn't seem like it.
All right, so you guys see the 3 different scenarios here? Give me a thumbs up if you see these 3 different scenarios. So it's basically the top is bigger than the bottom, the top is the same as the bottom, or the top is smaller than the bottom. Those are easy to remember, right? So it's just the degree. So do you know how to identify the degree of the top? What's the degree of the top here? 2. What's the degree of the bottom? 1. So if Let's see, that's this first scenario. If the degree of numerator is bigger than the degree of denominator, then there's no horizontal asymptote. Okay, so we just say no HA. Boom. All right. Okay, now finally we get to actually graphing here. And this is example 4. We are going to graph this. We're going to graph 2 over x minus 1. Starting simple. All right. So the degree here is 0. And the degree here is 1. So what does that mean when the numerator is less than the denominator? If the numerator is less than denominator, denominator is less than numerator, then the horizontal asymptote is y equals 0. Okay? So that means at y equals 0, we're going to have an asymptote, and you can put a little dotted line if you want all over the y equals 0. Okay? All right, so we're going to graph it. We're going to determine any points of discontinuity. Yes. So remember, my vertical asymptote. So we already figured out our horizontal asymptote, y equals 0. Our vertical asymptote is what makes this 0. So that is x equals 1. So over here, we're going to put another asymptote right here. See, that's where x equals 1. Okay? So there's a point of discontinuity at x equals 1. Since the numerator and denominator have no common factors, then the x equals 1 is our vertical asymptote. Since the degree of the denominator is greater than the degree of the numerator, the graph has a horizontal asymptote of y equals 0. Okay, so now we're just going to sketch it. So this is what it looks like. We're just going to draw a little, this is called a hyperbola. Not bad, right? That works. Okay. All right. So, and you might ask, well, how do you know it's like that and not like this? How come it's not like that? Well, you have to test some values. So you have to figure out what's true and what's not. So if you plug in a couple points here to figure out where it is, like you could plug in 0, 0 for x. Okay, if I do 0 for x, then I get 2 over negative 1, which is negative 2. So at 0, it's gonna go, it's actually, this should have been like this. Right. At 0, it would have been y equals negative 2. So this is graphed pretty poorly, but that's all right. That's where it would cross there. Okay, and if I picked like 2 for x, so 1, 2 for x, that would have given us basically 2 over 1, which is 2. So 2, 2. So this is where that graph is. So obviously I didn't do a very good job with these graphs, but they should be more like this type of thing, right? Ugh, that's terrible. But plug in some points so you have a better idea how to graph those. So that was an easy one. Let's do another one. I'm going to go down to my next graph here. Let's graph this. Y equals x squared plus 2x minus 8 all over x cubed minus 4x. All right, when in doubt, factor it out. So this is x plus 4, x minus 2, all over, take an x out, and you're left with x squared minus 4. And then you can factor that. So that's x plus 4, x minus 2 all over x. And that's x plus 2, x minus 2. Okay. All right. So these x minus 2's cancel. That's nice. But before we determine too much, look, we've got a degree of a denominator is greater than the degree of the numerator. So that means my HA is y equals 0 again. All right. And then my vertical asymptote is a little different. So the things that didn't cancel are a couple things. Look at this. So x equals 0 and x equals -2. All right. So on my graph here, my vertical asymptote are at y equals 0 or x equals 0. Okay, so there's one of my vertical asymptotes. My other vertical asymptote is at x equals -2. So right there. And then my horizontal asymptote is at y equals 0. Okay, so now it's like, all right, well, how do we graph this? Well, so the x-intercepts of a rational occur when, so you can figure out some x-intercepts and y-intercepts, but if there's a horizontal asymptote at y equals 0, then the x-intercept, that's going to be tricky. All right. Let me just backtrack a little bit here. So the x-intercept, calculate the value for. So basically, we're just plugging in values here. So if we just set x equals to 0, well, that is going to mess everything up, isn't it? So let's pick some other values here. So if we go here and pick like 2, so at x equals 2, we're going to have 6 over, let's see, 2 times 4 is 8, so 3/4. So at 2, 3/4, looks like it's right there. Okay, and then just pick some other values. And once you do that, what you end up having is, hold on one second here. Yeah. Okay, so we're just trying to figure out where y equals 0. So the x-intercept would be -4. So at -4, this is where it's going to touch the x-intercept. It's not going to touch it over here because that's where it gets us into trouble. Okay, so there's a point. We also had another point there. So basically your graph is going to look like this. And then down here is going to be this weird little thing here. It's going to look like this. And then this one is going to look like this. So it's a little crazy. Now, don't worry, because even on standardized tests and stuff like that, you're not going to be expected to graph something like this. You just need to be able to identify them. So what you're looking for is your vertical and horizontal asymptotes. All right. And then you just have to test some points that are around the asymptote so you know which way to draw and things like that. So don't stress too much on these problems. The biggest thing is just identifying those asymptotes and knowing where to draw them. But that's it. That's lesson 100.